Hello. Today's video lesson deals with lines and planes in space, this will go over some of the basic principles when working with that topic. What we start with is there's a point, it's on a line, and it's perpendicular to a plane. So we're given the equation of the plane, we're given the coordinates of the point, but we're not given anything about L. So naturally the first question is, find the equation for L. Now it says Cartesian. Now remember, Cartesian equations are equations that will have the x, y, z as the variables. Now, there's a step in between getting this information and finding the Cartesian equation, and that's the vector equation. So that should be the most straightforward piece. The most important thing that you need to remember regarding the equation of a plane is that the coefficients of the variables on the plane or equation represent the vector that is the normal to the plane. There's a proof of this, and this was discussed in class, but it's really helpful information. If you're given the equation of the plane, then you automatically know a vector that is going to be perpendicular to the plane. So it's like free information. Now, if this is the normal to the plane, then this is the direction of line L because the normal is perpendicular to the plane. So this is the direction vector, and we can convert the point A into a position vector, which is a solution to line L. Therefore, we can say the line L represents all x, y, z vectors that start at point A, or vector A in this case, and then we have the parameter time, and we'll head off in this direction. So this is the vector equation, and recall that to convert the vector equation to a Cartesian equation, we simply extract each dimension as functions of time, and then solve each for time, and since they're all the same time, we set them equal, and we get the equation of the plane in Cartesian form. Now for part B, we need to find the intersection of line L and plane pi. Before we do that, I want to remind everybody that GeoGebra is a nice little software that enables us to be able to visualize some 3D things. This is harder to do cognitively, and it's harder to do on pencil and paper, but when you see the plane mapped out for you like this, it's going to give you some confidence and some understanding of what you need to do. So to demonstrate, for example, we have, of course, our XYZ axes. I rotated it so we could see the point A, which is down here in the corner. So the equation of the line that I found is shown right there. The point that I'm given is right there, and the turquoise represents the plane itself. So, got ahead of myself right there. What we're looking for in part B is the coordinates of that point right there, or in other words, the vector position of that point right there. It didn't specify, so we're going to express it in as in vector form. You can even see that this point of intersection, you can kind of see that it's 2 over on the y, and it's 4 down on the z, and it hasn't moved at all on the x. So you can kind of see what kind of number you should get to find that intersection. To answer the question, all we really have to do is take our parametric form, which has x, y, and z all in form of time. So we replace x, y, and z with these expressions of time, and what we'll be left with is an equation with just t. We find out time t is equal to -1. What does that mean? Well, we take the vector equation of line L, replace time with -1, and this is going to create the exact vector position of the intersection. So in other words, what this is telling me is the line L meets the plane pi when time is -1. So to find that point, we put -1 in for time, and oops, so I got ahead of myself there again. Boom. There's the point. The vector is 0, 2, -3. So once again, we go back over here, and we find 0, 2, -3. It's again consistent with the fact that we've gone neither up or down on the x-axis. We go 2 up on the y, and we go 4 down on the z. And that takes us to what clearly shows this is the line on one side of the plane, and then we hit the plane at this exact spot, and then move back through space. So I feel really confident about this result. On to part C. Part C says point. Oh, I forgot to do part C. I just jumped to part D. So I'm just going to talk you through part C really quick. I'll go back to that picture of the plane. Or actually, let's go back to my answer from before. If we go from point A to the plane pi in -1 time, all we have to do is double that time, and we will be at the other side of the plane exactly as far away. So basically, for part C, all you have to do is evaluate the plane at t equals -2. So I could do that real quick here. We'll have, for part C, x, y, z, z of course, if you're American, -3, 1, or sorry, 3, 1, -4, right there, and, sorry, bear with me, we're going to put in plus -2 times the 3, 1, negative, or -1, -1. Boom. So what this should do is give us the values for x, y, and z, which, if I can do some quick mental arithmetic, is going to be -3, 3, and I'm guessing -2 here. And so once again, we can go back to the graph and see. I'm not going to draw it out because it could be pretty painful, but maybe I will. We're going to go over -3, and then we're going to go over 3, and well, I'm not going to try. Just trust me. So I wasn't planning on this. I missed something when I was creating the slides. So anyway, sorry for the distraction. I hope you don't have anywhere important to be. Anyway, for part D, it's nice and green for us. It means go, go, go. It says the point B has coordinates 1, 1, 1, show that B lies in the plane pi. So all I have to do is put in 1 for each of the variables and show that the equation is actually true. So point B is in fact a solution. Now, it's almost misleading that this is red because it says find the distance between B and line L, so point B and line L. Now, it might be a little bit challenging if, first of all, you think that it's red, it must be the most difficult part of the problem. Maybe the most difficult part is conceptualizing. So what I want to do here is to map out the point B. Let's see, hold on a second, bear with me. There's the point B. And there's the point C. Actually, let's do it from here. There's the point B, there's the point C, and there's this vector that can join points B and C. So if you actually visualize it, you could even see in this picture that clearly BC is perpendicular to line L. In other words, the answer to an earlier question where I found the position 2, -3, I've already got enough information to be able to find the distance from B to line L. I already know that they're perpendicular. So all I have to do in my work is just do the distance formula. So we'll have from 1, 1, 1 to 0, 2, -3. We're going to have 1 minus 0 squared, 1 minus 2 squared, and 1 minus -3 squared, giving us the square root of 18, or 3 square roots of 2. So that is in fact how long that particular line segment is. Now, you can estimate that and check it out with the graph, but here's the real question. Is this really the shortest distance? Is my assumption that these should be perpendicular actually true? And to answer that, I just verify that the vector that joins point B with 0, 2, -3, that's point C. So this is the line BC, or the vector BC, and this is my normal vector, which is perpendicular to the plane. And when I dot product the normal vector with the vector BC, I do in fact get 0. You can visualize that over here, that my solution set, let's see, turns out to be -1, 1, -4, and therefore we can see that these two are perpendicular to one another. And the distance is nice and easy to find. So I guess I kind of lost myself there in trying to justify. In my own head, it made a lot of sense, and it really does make sense. It just didn't articulate it very well. But the fact of the matter is, E is harder to think about, to cognate, than it is to actually calculate. The calculation is really easy because we're given, or we found part C, we're given B, just find the distance. Anyway, I hope this is helpful. Thanks for watching.